As we continue to consider how to find a spanning set for a particular subspace, let's consider subspaces of matrix vector spaces. So if we want to find a spanning set for M2, the collection of 2 by 2 matrices, I like to start with a generic element. Oops. And so a generic element of M2 looks like A, B, C, D, and there's no constraints. There's no relationships that have to exist between A, B, C, and D in order for this to be a matrix in a 2 by 2 matrix. It's just that's it. There's no condition. So then I say, okay, so how could I build a critter that looks like this? And so the simplest thing to do would just be to sort of pull it apart. So then I can see each of those A, B, C, and D as being a scalar multiple of something. So then I can rewrite the original matrix as some linear combination of stuff. So we've got this. And so then that tells me that M2 is the span of 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 1, 0, and 0, 0, 0, 1. So I'm not writing the zeros because I like to call attention to the fact, or to the part of the matrix that's non-zero. Well, that and I'm lazy, but there you go. So now suppose we needed to find a spanning set for the 2 by 2 upper triangular matrices. So let's call this U for upper triangular and 2 for the fact that it's 2 by 2. And so this is going to be all of the elements of M2, which are upper triangular. Okay. So then I would say, well, then what is a generic element of this vector space look like? So this is in fact a vector space, right? Yeah, maybe I should have pointed that out at the beginning, but recall that the upper triangular matrices form a vector space, so it's perfectly legitimate to ask about what is a spanning set for this vector space. And so let's see, so for it to be upper triangular, it just needs to be the case that I have a 0 here. And then the other things can vary freely with no constraints, relationships, or dependencies between them. So anything like that. Okay. So this I can write as A times this matrix plus B times this matrix plus C times this matrix. All right. So then that tells me that U2 is the span of 1, 0, 0, 0, and 0, 1, 0, 0, and 0, 0, 0, 1. Okay. So now I have a spanning set for U2. Now let's maybe do something a little bit more interesting. Let's look at find a spanning set for, let's call it S3. This is going to be the 3 by 3 symmetric matrices. So these are all the elements of M3 that have the property that they are symmetric. So in other words, we need A transpose to equal A. Okay, so again, I want to find a generic element. What does something that lives in S3 look like? Well, thinking back, the condition here on the coordinates is that Aij needs to equal AJI, because AJI is AIJ transpose. So on the left here, we have the ijth entry of A, and on the right here, we have the ijth entry of A transpose. And so those have to be equal, right? So that means that the condition I'm going to be looking for is this one right here. Okay, so what does that mean? Well, if I start sketching out my generic 3x3 symmetric matrix, I can put an A here, and that's not apparently related to anything. I can put a B here and a C here, but then when I get to my next one, in order for this matrix to be symmetric, I no longer have the freedom to choose what that gets to be. It's already been determined for me back here. If I don't put a B in this position, it won't be symmetric. So I better put a B there. Now, the diagonal gets sent to itself when you do a transpose. So D has to equal D. Okay, that's fine. No information there. What about this guy? He's not related to anything that's on the board yet. What about this guy? Oh, yeah. A31 has to equal A13. So that means this has to be C. And then this has to be E. And then this last guy can be whatever the heck you want. So this is the most general thing that I can have for a 3x3 symmetric matrix. Okay, and so that tells me then that I can write a 3x3 symmetric matrix as a linear combination of this matrix plus this matrix, and this one now has two entries which are non-zero in it. And so does this one. C is in 3, 1, and 1, 3 position. There's a 1. And D is our guy in the center. And E is now bottom center and back right. And oh, and I ran out of room. And F is just the guy on the bottom left. Okay, so then that tells me that S3 is the span of these matrices. Oops, I forgot D. Whoop, that guy. There we go. Not that the order matters. I can write them in whatever order I want, but it's just less clear if I write them in some crazy scrambled order. Okay, and so let me just use this example as an opportunity to stress what I mean by generic. So, for instance, if I had A, B, B, C, 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 D, D, E. This is a symmetric matrix also, but I've lost some freedom here because it's possible to have a symmetric matrix where this particular entry does not match the ones that are on the same off diagonal like this. And so if I were to choose this as my generic element, and so this is a non-generic one, right? Because I'm imposing some additional condition. I lose some freedom, and if I have, this would lead me to saying, okay, so then the span is going to have things in it that have this one, this one, this one, this one, and this one. So I would mistakenly believe that this is a spanning set, which is not true. And the key point is that if I have some symmetric matrix like 2, 1, 1, 0, 3, 0, negative 1, negative 1, 5, this is a 3x3 symmetric matrix, but it is not in this span. So this right here fails to be a spanning set or fails to span S3. It's not good enough.